Welcome. The title of today's notes worksheet is Square Roots. We will begin by looking at a different family of expressions over the next couple days, specifically the radical family of expressions, but we will go through the same process. We'll do some simplification, manipulation, and some operations dealing with this particular family. So we'll go ahead and start it out with a couple properties that I see at the top of your paper. If you go ahead and highlight those, that would be great. So what's called the product property and the quotient property dealing with square roots. And you can kind of see this abstractly written on your paper here. But basically a product written underneath the root can be broken up as a product of the two roots right here. And a quotient written underneath the root can be broken up into a quotient of two individual roots. So we'll be kind of going this direction and this direction depending on what the problem asks, and same with the quotient property, this direction or potentially that direction. So let's do just a couple examples here. If you have a calculator handy, that would be great. You can confirm a couple of these things as well. But this is definitely a property that comes up. So something along these lines right here, really just making up numbers for us. Square root of 2 times 3, so square root of 6. According to this particular property, that should be the square root of 2 times the square root of 3. Again, individual product over here, and then put them together underneath the root right over there. So why don't we go ahead and bring that calculator up at this time. And again, please confirm it yourself and get used to really working with these calculators in great detail. I'm going to go ahead and just type in square root. So I hit the second button and this button right here. So square root of 6. And of course I get that decimal approximation right there. That looks great. Now according to the product property, that should be equivalent to the square root of 2. Close that off, by the way. And then times square root of 3. And we end up getting, of course, the exact same value. So product property is probably the most prevalent property that we'll use over the next couple days, so just keep that in the back of your mind. Putting them together under one root or separating it into two roots. Let's go ahead and put an example for the quotient property right here, guys. Of course, if you want to change numbers, that's perfectly fine. I'm just going to do something simple. How about something like that? Square root of 7/5. So that should be equivalent, according to this particular property, of square root of 7 over square root of 5. Again, so separate them into two roots. Keep that fraction symbol, of course. And let's go ahead and do that right up here. So I'm going to go on back and again hit that second and square root button. And 7 divided by 5 there underneath that root. And we get that decimal approximation right there. And then, of course, what I'm going to do is hit square root of 7, close that on off. Then divide by the square root of 5, close that on off, and notice, of course, we do get the same thing. So just wanted to confirm exactly what these properties said in a somewhat abstract form over here. You see them numerically, of course, over here. So we'll go ahead and utilize those. I do have one investigation to get us kind of thinking about the manipulation piece dealing with square roots. So we'll go very concretely initially. Dealing with the perfect squares numerically, and then we'll go ahead and get a little more abstract with those algebraic expressions that you see. So let's give it a try. Now, first perfect square, 1 squared is 1. In terms of simplification, that is going to be of no use to us whatsoever, but it is the first perfect square, so I'll go ahead and put that in place. And then 2 squared and 3 squared. And guys, create your list. You can probably do this faster than I can. So what do you say we go up to about 15? That's probably when I'll run out of room anyway. Should know your first 15 perfect squares, and even beyond that, of course. But let's go ahead and get those in. As I said, beat me to it if you want. Make sure I've got all mine. And 11 squared, 12, 13, 14, 15, how about a ... on the end of that? And obviously, again, just keeps going and going and going. I should be comfortable with those, as I said. Should be comfortable really through 25, I would say. But for our purposes here, you probably won't see too many beyond this. So not a problem. Let's get those numbers in place, though, and you should be able to really recognize those as we go through this process. All right. Numbers, not a big deal. Now what I'd like to do is focus on the abstract piece, the algebraic expressions. And so what I'm thinking about here is all of the perfect squares in a particular variable. Now I'm just going to go with our generic variable x on this, and so I'm thinking about all powers with base x, which one of those would be perfect squares. So I'll start us off here and then get you kind of thinking in the right direction as to what would come next and what would come next and what would come next and so forth. All right, so the first perfect square is x squared, of course. Any number squared, I guess by definition, any number squared will be a perfect square. So this representing our any base, that's perfect. X squared is a perfect square. Now here's what I guess I would ask you. What do you think the next perfect square would be in our base x? What do you think? X to the what would represent the next perfect square? All right, think about that. Is it x to the third? Is any number cubed a perfect square? Well, 2 cubed is 8, and 8 is not a perfect square, so no, I don't think x cubed would be our perfect square. What about x to the fourth? Think about raising a number to the fourth power. Is that a perfect square? Well, if I do 2 to the fourth is 16. Oh, wait a minute. 16 is a perfect square. 3 to the fourth. 3 to the fourth happens to be 81. Oh, wait a minute. 81 is a perfect square. So when you see this, any number to the fourth power happens to be a perfect square. So our next little piece in this pattern is x to the fourth. Great. I hope that makes sense. Okay, now we're going to get the next one. What is the next perfect square? Well, x to the fifth, I don't see it, but I see x to the sixth actually being the next perfect square. Think about that. Take a number and raise it to the sixth. I'll do 2. 2 raised to the sixth happens to be 64. And look at that. 64 is on our list. So anything raised to the sixth is a perfect square. And I'm hoping you're starting to see the pattern here as what emerges with those exponents. So just to expedite this along a little bit, everybody, the next one would be x to the 8th. The next one would be x to the 10th. The next one would be x to the 12th, etc., etc., etc. Okay. Now we're going to go one step further with this, just to kind of write a couple things below. If you want to write it in, I would recommend it. If you don't, that's quite all right. But I guess I would ask us, what would be the square roots of each of these powers? Another way to phrase that would be, what squared would give me each of these terms that you see that I'm circling on your paper? Okay, well, this one's easy. It is, of course, x that's being squared to give us x squared. So the square root of x squared is going to be x. What about this one, though? What is it that's being squared in order to get x to the fourth? Well, I hope you would agree, based on just the power property, x squared would be x to the fourth. So if I asked you for the square root of this right here, you would tell me x squared. All right. What's being squared to get x to the sixth, everybody? Well, it's got to be x cubed. Power to a power. 3 times 2 is 6. So if I asked you for the square root of x to the sixth, you would tell me x cubed. And I'm hoping you would see the pattern there. That means that the square root of x to the 8th is x to the 4th. And again, I'm just going to go ahead and dot this. All right. Now again, I think this is helpful for the way we're going to manipulate some of these expressions. If you know this in great detail already, great, wonderful. Hey, let's bring up the calculator just for a sec to verify a couple things. So we made this list, and I basically told you that any power, essentially, on this list is a perfect square in any base. So for example, if I said any number raised to the 10th, something like this right here, should be a perfect square. Well, let's test it out, everyone. So I'm going to do 2. I'm going to raise it to the 10th. 2 to the 10th is 1024. Now, that should be a perfect square. So let's go ahead and take the square root of that number. And yeah, 1024 was the square of 32. Does that make sense? Cool. Let's try one more. How about 3? Let's raise it to something else on this list. Oh, how about to the 8th? So anything to the 8th should be a perfect square. So 3 to the 8th is 6,561. This should be a perfect square according to what we just developed. So I'm going to take the square root of that and end up getting 81. So this is the perfect square of 81. All right, good. I hope that kind of makes sense because, again, we're going to utilize that piece momentarily. Let's move on to that next example then. All right, so we're going to start with the simplification piece. And I have two methods to go ahead and pull this off. The number one is knowing your perfect squares, and that's why we developed that list above. And I'm probably going to gravitate towards that. I have another method if you're interested in exploring here. I call it the dating method. It's kind of silly, but it works. So I'll go ahead and show you that. And again, if you like that, great. If you don't like that, no big deal whatsoever. So let's do example one together. I know you did this in previous courses, just working with square roots and being able to simplify them. So let me just go ahead and go over how to pull this off. So we're going to use the products property here to simplify square root of 24, meaning we're going to pull out the perfect square that goes into 24. So if you look at the list above, of course, you would say 4 goes into 24. So another way to kind of say this is 24 is really 4 times 6, which according to the product property is square root of 4 times square root of 6. We've confirmed above that that works for any square roots. So here's our product, now separated into two roots, of course, product in between. And what is the square root of 4? Well, 4 being a perfect square, its square root is 2, and I end up getting 2 square root of 6, and that, as you recall, would be the simplified exact version of square root of 24. Great. And that's pretty much what I'm looking for here. Now, again, I'll show you the dating method. If you like it, great. If not, no big deal. So it's dealing with something that comes up in number theory a lot, what's called prime factorization. And so what I'm going to ask you to do is take 24, and we're going to break it down into a product of its primes. So nice and easy, a couple branches here. I think we would all know that 2 times 12 is 24. And guys, 2 is a prime, so circle that for me. And 12 we're going to break down as 2 times 6. 2 is the prime, circle it. And last but not least, of course, 6 breaks down to 2 times 3. Both are primes, so circle them both. Now here's why it's called the dating method, and as I said, it's pretty silly here, but I don't know, I think it works. So the idea being is if a number has a date, it gets to go out and have a good time. So for example, the 2 has a date. It is formed as a couple. And so the 2 as a couple gets to go out and have a great old time. So couples go out, singles have to stay home. They don't have a date, got to stay home. So guys, does everyone see the 2? It's a single 2, and so it has to stay home under the root. Do you see the 3, everybody? Well, that 3, unfortunately, is a single, and so it has to stay home. And so it goes underneath the root. And then the 2 as a couple got to go out. 2 times 3 is 6, and there's your 2 root 6 right there. So couples go out, singles stay home. Kind of cool. I kind of like that piece, but as I said, just work whatever works for you. And here's your thing right here. You know, 2 times 2 is really 2 squared. So 2 as the value getting us the perfect square comes out. All right, hey, I'd love for you to pause the video actually and see if you can just do a couple of these quickly. So square root of 120 would be great, and square root of 72, if you could pull that off for me. And then I'll probably rush through both methods there, but you should be able to work with these. Well, let's see how you did. I looked at this, and I kind of looked at my perfect squares list from above, and as a matter of fact, I only found that the largest perfect square going into 120 was 4. 4 times 30 there. And so product property, 4 times 30. And of course, square root of 4 is 2. And so I got 2 root 30 on this one when all is said and done. Again, I'll do the dating method just one time here pretty quickly if you tried it, and maybe it worked, maybe it didn't. But I like this. There's a lot of good number theory that goes into these prime factorization diagrams. So 2 and 30 for me, 2 and 15, 3 and 5, and primes right there. And if you kind of take a look, again, couples go out. So as a couple, the 2 got to go out. Singles have to stay home. 2 times 3 times 5, and 2 times 3 times 5 is 30. Pretty awesome, huh? Great number sense. Good stuff all the way around. So just trying to show both methods. Hey, over here, let's just see how you did quickly. This one you have to be careful because there are a couple perfect squares that go into 72. You do want the largest to make sure it's completely simplified, which I believe is 36. And so 36 times 2 I think is our winning combination. And everybody's square root of 36 happens to be 6. So 6 root 2 would be the simplified version right there. If you did 4 into that one, now don't write this on your paper, but if you did 4, you would do 4 times 18, and you'd say, oh, 2 root 18, isn't that simplified? And I agree, it is more simplified theoretically than what we have up here, but there is a perfect square that goes into 18, of course being 9, so this can be simplified further. So you would want to kind of simplify it until there is no perfect square that goes into your value underneath the root. Hopefully you kind of remember that again from previous courses. Hey, let me just run this by as fast as I possibly can. Just the dating method on this one. So 2 and 18, 2 and 9, 3, 3. And again, you get to see, as a couple, the 2 got to go out. As a couple, the 3 got to go out. And, uh-oh, poor little single, got to stay home. And there's your 6 root 2. Pretty awesome, huh? Alrighty. Well, let's go ahead and see if we can get a little more abstract with this, just working with some others, and then we shall move on to the next little skill set. So, again, I think I had mentioned this, but I probably will start to gravitate a little more towards the perfect squares approach. But if you want to do the dating approach even with the variable, it still works. Please feel free to inquire about that. But I guess here's how we're going to pull this off, or at least how I'm going to pull it off. I'm going to put all my perfect squares into one radical and all the remaining factors in the other radical. And that works because of the product property. So I'm going to write this as a product of this root times this root. It just so happens I'm going to be selective about it. All the perfect squares are going to go in here, and all the remaining factors are going to go in here. And so as I look at 50, well, we all know, of course, we can break down 50 into a product of factors. And of course, in this case, the largest perfect square that goes into 50 is going to be 25. So I'm envisioning a 25 times 2. 25 times 2 is 50, perfectly legitimate according to the product property. Now, here's where the variables come in, and you might want to look at your list from above. What is the largest perfect square that divides into x cubed? Well, according to that list, I believe x squared goes into x cubed. And so the question, of course, is x squared times what would give me x cubed? Well, the remaining factor would be x to the first. And so there are kind of some ways to play around with this a little bit, but the bottom line here is what we're going to do is take square root of 25 and get 5, square root of x squared. So what is it that's being squared in order to get x squared? And it is, of course, x. And then we have this right over here. Good. And so we'll go 5 times x times root 2x right there. And that would be considered the more simplified version, pulling out the perfect squares from the value underneath the root. All right. Good. Let's move on to part B. So part B is product of those two. Now this might seem a little strange on this one, but rather than breaking each one individually and kind of doing perfect squares and so forth, I find it more convenient, and you may agree or disagree on this, to go ahead and put them together initially, again, because we can go back and forth on this, and then break them apart according to the way we want to do it. So here's what I mean by that one. 6 times 3 is 18, so let's just do it as a product. X times x to the 5th is x to the 6th. So this is equivalent to this right up here. Now this is nice and consolidated for me, and I can play around with this because now what I'll go ahead and do is try to get my perfect squares in one and my remaining factors in the other. And so as a result, now I can break it apart according to the way I want to do it. As opposed to 6 and 3, I'm thinking 9 and 2 because 9 is a perfect square. Again, it's up to you. If you want to explore a different approach on this, that's fine. And by the way, if I'm looking at the variables, what is the largest expression that goes into x to the sixth? Well, as a matter of fact, x to the sixth is a perfect square. That's what we determined. Any base raised to the sixth power is a perfect square. And so now it looks like we've got some good stuff going on here. 3 square root of x to the sixth, as we decided up above, is x cubed times square root of 2. Looking good. All right. So I hope that product property on A and B worked out well. I think we'll go ahead and try just a little bit of the quotient property here, and then hit the back side and try something else. So same thing. Put things together, break them apart according to your whim, whatever works for you. So I would look at this, and I would first think about it in these terms right here. Kind of just putting it together helps me visually. It's up to you how you want to play that out. And then I kind of see this as underneath the root here. I can play around this with this. 48 divided by 6 is 8. X cubed divided by x is x squared. And now it's getting more simplified as we speak. Let's go ahead and play around with this and see what perfect squares we can pull out. And so I go ahead and do my product property at this point, just from what I have. And I'm getting a 4 and 2 and an x squared right here. So make sure that works for you. And then, of course, let's simplify this piece right here. Square root of 4 is that. Square root of x squared we will dictate as that. And now I have that piece right there. Okay, nice. Again, it's just manipulations of expressions, different ways to express them. I kind of like this one right here, so let's go ahead and do part B. Same deal. I'm going to go ahead and do this. If you can kind of expedite this along, that's totally fine. But basically, we've got all this stuff underneath one root. Let's see if we can kind of simplify that a little bit. Maybe consolidate some of those powers base x, and then also do the same thing on those powers base y. I'm going to go throw a little y to the first right in there. And let's see what we can do. Let's see if you kind of know your exponential properties and see if we can work this out. Hey, look, x squared times x cubed is x to the fifth. So the top is x to the fifth, divided by the bottom, which is x to the fourth. And x to the fifth divided by x to the fourth should be x. So underneath the root still, I'm going to have an x. And then let's see, I have y to the first divided by y to the third. Well, that should be y to the negative second, right, everyone? Y to the negative second. And make that positive, so that would bring that on down. And so that would be this underneath the root at this stage. Okay, and again, it's looking better. Let's see if we can pull out anything that is a perfect square. I look at the top, and I don't think I can do much with that. But I look at the bottom, everyone, and I'm wondering if you do the same. Down on the bottom, I just have the square root of x squared. And again, I don't know if this helps or not, but this is this. Again, feel free, break them apart, put them together, whatever works for you. Just visually, this, of course, is this. And if it helps in that case, then that's just square root of x. Can't touch that. But this, obviously, we can work at as y squared is a perfect square. And by taking its square root, we'll leave it as y. Okay. Nice. So you get to really play around with it just based on what you see. Putting things together, breaking them apart according to the product and quotient properties. All righty. Now, guys, we're going to take a look at one more skill set here with a few examples. What's called rationalizing a denominator. And as it says, we're going to eliminate the root or the irrational number in the denominator. And there are two types that we're going to take a look at. We'll go ahead and get into those types momentarily. If you don't mind, just a very quick explanation on kind of the convention for doing that, really why we rationalize a denominator. And it's based on really something along these lines right here. So don't have to write this down. Just bear with me literally for 60 seconds, and I'll see if I can do this justice for you. So this would be something that we would rationalize. And it all comes down to understanding what a fraction means conceptually. So, you know, this 1 over square root of 2. Square root of 2, of course, we all know as an irrational number. What that really means, a fraction is just division, right? And so think about this. What division really means when all is said and done is that we are dividing a finite length, So that would be the numerator in our fraction here, really what we would call the dividend. We're dividing a finite length into countable pieces. Okay, something along these lines right here. Unfortunately, this expression really doesn't make sense because the divisor, which is the countable pieces part, is not a countable number. We simply can't count square root of 2. And so it's not something that really makes sense conceptually. But when we rationalize it, and I'll just tell you right off the bat that this would be the rationalized version of that, this makes just better sense. This is basically saying we have a finite length of square root of 2 units, which we actually can create. And what we're going to do is divide this into 2 pieces. That's the idea. This is a countable number. We can divide this into 2 pieces. That's what division really stands for. But when we see it in this form, it really doesn't make sense. We can't divide it into the square root of 2 pieces because this is not a countable number. So again, if you want to explore that in a little more detail with me, be happy to explain it further. But that's really, you're making the fraction have more meaning. That's the bottom line, by rationalizing the denominator. Wonderful. And so guys, let's go ahead and do it. As I said, 2 types. Let's see it in action. This one is a pretty straightforward one. So the first one just says, multiply by the root in the denominator or any root to get a perfect square. We are going to rationalize the denominator. So at this stage, you're basically saying something like, I'm going to take a finite length of 5 and divide that into square root of 3 pieces. And again, it just doesn't have a lot of meaning. It doesn't make sense because square root of 3 is not countable. So what we're going to do now, guys, is rationalize it. And the easiest thing to do here, and I'm sure you've seen this before, is to go ahead and multiply the top and bottom. Because it's a fraction, we have to do the same thing to the top and bottom by the square root of 3. Because, well, I'll do the top first. 5 times square root of 3 is just 5 root 3. So just a product of those 2 values, one an integer, one an irrational number there, and we just leave it like that. Now the denominator, everyone, is root 3 times root 3, which of course according to the product property means square root of 3 times 3, or square root of 9, and the square root of 9, of course, is 3. And now it's been rationalized. Another way to look at this is the square root of 3 squared. Something like that. I hope you all see that you get 3 there. And again, I would just argue that this fraction just has more meaning. So this is a finite length, 5 root 3 units, and we would divide that into 3 pieces. This length divided into 3 pieces. It just makes better sense. Anyway, that's your answer. That's rationalized. Cool. This one could be done a couple different ways. Again, leave it up to you. But I'm just trying to create a perfect square down there. So as I look at 18, I don't know, one way to do this is think about 18 times what would give us a perfect square? Well, 18 times 2 would give me 36. That's just what I'm seeing. And so as a result, if I can multiply each of these by the square root of 2, well, the top, of course, is 3 square root of 2. And then the bottom would be root 18 times root 2, or root 36, and root 36 is 6. And so something along those lines right there. This would simplify. Again, just good algebra. What works, what doesn't. You can do 3 over 6 there as a 1 over 2, and you get this square root of 2 over 2. By the way, this happens to be a number that comes up a lot in trigonometry. You will definitely see that in the future. Cool. And again, just in terms of this, this one doesn't have a ton of meaning, but now when it's simplified, again, it clicks better. All right. Oh, by the way, there was another way on this one. Again, always just helping you explore different options. Square root of 18, I don't know if it caught your eye, but that does simplify, doesn't it? You know, square root of 9 times square root of 2. And then these cancel, and you end up getting 1 over square root of 2. And you rationalize, and I actually showed you this number already. But there you go, guys. Square root of 2 on top. And root 2 times root 2 is root 4, or really just 2. So regardless, again, different ways, please let me know. As you work through it, just call me over and be like, hey, Mr. Meyer, does this work? And I'll let you know. Hey, let's do number 2, a little more complex here. This is an algebraic technique or a trick that comes up quite a bit, working with what is called the conjugate. So a very brief explanation. So a conjugate has the same first term and the opposite second term. Just jot that in there if you would, and I'll show you what that looks like. So it just says multiply by the conjugate of the root if there is a binomial expression in the denominator. So let's try that on 6. So nice and easy to start. This obviously is an irrational number made up of a sum of an integer and this irrational number right here. But again, as a whole, this is an irrational number. We're going to rationalize it. And so what we're going to do to get rid of it is multiply by its conjugate. Same first term, opposite second term. So if it's 3 plus root 2, the conjugate would be 3 minus root 2. Okay, now again, whatever I do to the denominator of a fraction, I do have to do to the numerator because it's like multiplying by 1, right? I'm just taking this fraction and multiplying it by 1. And so I'm not changing its value, I'm changing its form. Great. Well, guys, the numerator. 1 times this is that. Cool. And then what we have is a little FOIL. And watch for the whole reason for doing this, by the way. This technique works out nicely. If I asked you to FOIL, you would do 3 times 3, which is 9. You would do the outside, which is negative 3 root 2, and the inside, which is positive 3 root 2. Oh, awesome. They cancel. Just be careful on the last. You've got root 2 times negative root 2, and root 2 times negative root 2 would be negative root 4, or negative 2, minus 2. And I'm hoping you see that. If you don't see that, please call me over and let's take a look. But 9 minus 2 is going to give us the 7. And there you go. Here's a finite length divided into 7 pieces. I like that. Very cool. All right, so let's see if we can expand on that a little bit. And you see why that conjugate works out very nicely. I've seen students in the past, and sorry for going back to letter A here, they would just multiply by the root 2. And don't do this on your paper. In fact, I'm going to erase it. But thinking about, oh, if I just multiply the denominator by root 2, I should rationalize it. And you're right. In this case, they would rationalize this part of it, but wouldn't it just create another irrational part by doing this, 3 root 2? And so it doesn't have the intended effect. You wouldn't be rationalizing it. It would be incomplete. All right, so conjugate for these binomials. So with that said, guys, let's go ahead and see what our math is like. 2 root 3 minus 3. So there's our conjugate. 2 root 3 minus 3. Okay, guys, make it happen. Would love for you to pause and do your own math on this, but if you want to watch it all the way through, that's fine. So let's go ahead and distribute. 2 root 3 times root 3. Again, you can multiply the numbers underneath the root. And if it helps you, I'm going to kind of write this out a little bit. This is what this is basically saying right there. 2 times root 3 times root 3. And then minus 3 times root 3. I want to make sure I account for everything there. So that would be the numerator, which, by the way, I'm going to go ahead and simplify. 2 times root 3 times root 3. Well, guys, this is root 9, which is 3, and 2 times 3 is 6. This is 6. I hope you see that. Minus, now 3 times root 3 is really as simplified as it gets. I think that's your numerator. Now the denominator, let's go for it. We have to be careful here. First is 2 root 3 times 2 root 3. So something like this. I'm going to literally write it like this for you just to make sure we're okay in seeing it. That's the firsts, which we'll figure out in just a second. Now remember, just to shortcut this a touch, everyone, what happens to the outside and inside? Outside, inside, same terms, opposite signs. They're gone. And then as you can see, the last, 3 times negative 3, I'm hoping you're all right immediately me putting 9 there. Now let's see what happens with this, by the way. So 2 times 2 is 4. Root 3 times root 3 is 3. Everyone okay with that? So this is really 2 times 2, And root 3 times root 3, all multiplication. I'm getting 4 times 3, and so I get 12. Now, 12 minus the 9, there's your 3. Super. All right, let's do it. This is still, I think we can work with it. Always, just when you're working at these levels, you're always just looking to simplify further if you can. Just be careful. Do the 3's just cancel here? Nope, they don't. We've kind of talked about that piece. In order for things to cancel in a fraction, we need to talk about factoring first. So I would factor out in the numerator, the 3, and I would get 2 minus root 3. That's the only way things cancel out, is if they are in factored form. Now they go. And to make a long story short, 2 minus root 3 is a good answer. Okay. All right. Take a look at that piece. Just make sure it makes sense. I'm going to have to do just a touch of erasing here to kind of leave some room for this next one. Let's go get letter C. Here we go. There is your conjugates. I'm going to go ahead and FOIL the top. Again, maybe work ahead, maybe work behind. Don't be passive, though. You can do it. 1 times 1 is 1. Outside is root 3. Inside is root 3. Now, we're going to do this more on tomorrow's lesson, but I will tell you that would be a 2 root 3 at this stage. And in root 3 times root 3 is 3. Okay. Bottom, 1 times 1 is 1. Outside, inside, cancel. And you end up getting negative root 3 times root 3, which would be negative of the root 9. So there we go. All right, check those numbers, make sure they work. Let's start cleaning this up. I can put a couple things together. I get 4 plus 2 root 3 over negative 2. Very nice. This just probably runs in a very similar format to this last one right up here. The factor before you cancel, everyone, please make sure of that. So you get 2, and then 2 plus root 3 over negative 2. How does that look in terms of simplified? Probably just a touch more to go. 2's cancel. Do have that negative to deal with. And you can do this a couple different ways. I don't know, maybe just kind of dealing with that negative this way. Dividing each of those terms by that negative 1, which would be in the denominator. I don't know, maybe something like that would do. Coincidence that it was close to this right here, by the way, just kind of the numbers I chose for these examples. All right, look at those. Really some great math to be had on these. Just good manipulation of these expressions. Last one. I think I'll be very quick on this. Just, I don't want to overplay the time. So just very quickly, the early Greeks believed that the most pleasing of all rectangles were what were called the golden the golden rectangles, whose ratio of width to height is this right here. Rationalize the denominator for this ratio. All right. So how about this? Why don't I just kind of pull this off pretty quickly, just show you what it looks like. So you would do it one more time. Binomial expression in the denominator. In order to rationalize it, you would be working with the numerator there. It's conjugate, I should say, in the numerator and denominator. And so we end up getting something along these lines right here, where I do get 2 root 5 plus 1. I'm going to leave it like that just for a moment. And in the denominator would be root 5 times root 5, so that's 5. Outside, inside, cancel. Negative 1 times 1 is negative 1. Okay, look at that. So I get 2 root 5 plus 1 over 4. Let's go ahead and put parentheses around that. And does the 2, can it work with the 4? Yeah. And actually you see this number typically this way. Typically with the 1 out in front, not that it matters by any means. And the 2 over 4 just means over 2. And this happens to be the golden ratio, a number that comes up a lot in mathematics. We might have a chance to explore this before the end of the year a little bit. And I have a feeling you looked a little at this number in geometry. It is phi, sort of denoted by that Greek letter right there. And so phi is equal to the golden ratio, which is exactly 1 plus the square root of 5 divided by 2. And again, I won't go into this in too much detail. Let's wrap this on up. But if I was to kind of get a ballpark figure on what that would be, divide by 2. So roughly, again, as an irrational number, you can see the golden ratio is in about the 1.61 range, somewhere in there. Cool. Again, hopefully we'll have an opportunity. Now is not the time. Awesome. Well, I'll wrap this up at this stage. Thanks for listening, and please work with some of the practice problems and let me know how I can best assist.